As the well-known saying goes, behind every great CNC machine, there is a great controller. Except this controller's fairly modest really. Specifications not particularly high, it's not that high end, but it does work, and I guess that counts for something. Before we get into that, this is not a tutorial, it's not going to be a step-by-step guide on how to build your own control box. This is going to be just an overview of my control box, how I did it, some of the thoughts that I went through along the way, some of the principles you might want to employ in your own control box. So we'll kick off by talking about why do we need a control in the first place? What does it actually need to do? Now pay attention, this might be on the test. Okay, so start with the most obvious requirement, and that is we need some way to move this cutting tool here around in space. We need it to move forward and backward, left, right, and up and down. And we do that on this machine by the use of these ball screws. Now these take advantage of the principle of the inclined plane. So essentially we've got an inclined plane, gives us a lot of the mechanical advantage. That inclined plane is wrapped, in this case, around a cylinder to drive a ball nut backwards and forwards. So it's very similar to this, we've got this bolt and nut here. If we hold this bolt in bearings like that and then turn it, obviously you can see that that nut goes backwards and forwards. It's being pushed along by the inclined plane, backwards and forwards like that. Again, the inclined plane is wrapped around that cylinder. So to move our axis, to move our ball nut, we need something to turn this. For that purpose we can use an electric motor. There are various types available, but for today we'll just talk about the basic stepper motor, because that's what I have on my machine. So we won't go into servos and encoders and so on. We'll just stick with the basic stepper motor. So these work on the principle of rotating a very small but very well defined step every time they receive one pulse of electrical energy. The more pulses you send, the further around they rotate until they've done one revolution. If you keep sending them more pulses, they'll go round and round and round. So this property of the stepper motor is to turn a very small but very exact and very well known amount every time you send them a pulse. Makes them really handy, especially when you combine them with this ball screw that has a very well defined pitch. So the pitch on this ball screw is 5mm. So it's 5mm between the crests or the troughs, however you want to think about it. When you combine those two factors, you know how many pulses it takes to turn this ball screw one revolution, and you know that one revolution is 5mm of travel. You can have a very accurately defined motion control system. Most DIY machines, although not all of them, are what we call open loop control. This means the controller blindly puts out pulses and it assumes the machine is moving into the correct position. So let's say this bear is the controller, the chessboard's a CNC machine, and this Connect 4 board represents open loop control. He can't see what's going on. So the bear sends out signals to the drafts piece, so like this, and moves the axis around, and it blindly assumes that the axis is going in the location that it's been sent to. The bear assumes all is well. So the controller might be moving the machine around like this and jogging the axis around, and then as the axis gets closer to the edge, it might... So the controller's moving the machine around, and it might get really close to the edge and actually hit the end of travel like that. So we need some way of sending a signal back to the controller. So on my machine I've got proximity sensors. You can also use micro switches, these very cheap ones, or you can go for the industrially chunky ones which some people use. A little bit more money, but designed for the purpose. So the other thing we need to do is when the machine first wakes up, it has no idea where the machine is. It could be anywhere on here, so we need to do something called homing. So the controller needs to tell the machine to move to one end of the travel, and there's a switch there called a homing switch. On my machine that's a proximity sensor, and what it does is it keeps moving the machine towards that until it detects that position. So when it detects that it's just got right to the end of that travel there, it sends that signal back to say I'm at this position here. It repeats for the other axis. So now we know where 0, 0 is, and you repeat for the vertical as well. So that's called homing the machine, and we have homing sensors to do that. Yeah, I got 4 in a row. So to recap, we need to send out pulses, we need to send out direction signals so it knows which direction to move on the axis, We also need to tune the machine so we're not driving it too hard or not driving it with enough faults. Make sure we don't get any missed steps. We need to monitor the machine in case it goes too far either way, so we have limit sensors. And we also need a way of homing the machine to get it back to 0, 0, so we need some homing sensors as well. So in terms of what else, what other features should you consider? Well, they're the basics. The rest of it really depends on what you want to do with it and how you want to implement some of the additional functions. I think really it starts with a key one for me, which is how you want to handle the safety side of things. So machining is not perfect, things happen, and therefore in my view you really should fit an e-stop. I have two on my machine, so I have one on the front panel here, so this is a hardware e-stop, and then I have another hardware e-stop in the same chain on the front of the machine down here. So these are hardware e-stops. What that means is they just completely cut power to the drives. Now they will also send a software signal to tell the software that there's been an e-stop, but effectively they kill power to the drives and they effectively then stop the machine dead in its tracks. Now it goes without saying, people always say that and then they say it anyway, so here goes. Do not rely on software e-stops. For example, I could press the escape key on the keyboard, or there's the stop command on the screen. Both of those would be a software e-stop. In my view, that's a little bit dangerous. You should always go for the hardware e-stop. Don't go for the software e-stop because it might fail just when you need it. Okay, so what else might you want to consider? Well, there's the spindle start stop. I've got these buttons configured so they connect up to the inverter, to the control panel. I've also got a potentiometer here that controls the spindle speed, so I'm doing this manually. Every time I run the program I just set this. You can also do that automatically in the G code. You can have it run those features from the code automatically. Over here I've got program cycle start, the feed hold and the stop, and then reset to go back to the code. Same with feed rate override and feed rate reset. Those I was going to implement via Pokies, which is a keyboard emulator board. And I actually purchased the board some time ago, and I've got a slot for it ready to go in. And essentially what that does is it emulates keyboard presses, so when you press that button it does the keyboard shortcut for cycle start, and so it's sort of a way of controlling the software from the front panel. I've never got around to implementing it, but it's there one day should I ever decide to. And also on here I've got an auxiliary switch for the lighting. It's nice to have a little bit of light underneath the machine. And then this switch here starts the water cooling pump and the fan for the spindle. So that's off at the moment. I've got on. I did have a feature reserved there to automatically switch it on, but in the end I've never wired that one in. So as you can see, there's lots of different options and lots of different functions and features that you could consider on your machine. I quite like the manual approach because sometimes I do a little bit of manual milling, like a sort of a semi-automatic milling. So I use the CNC machine in kind of manual jog mode and use it like a milling machine with a DRO effectively. And it's quite nice just to go in and start the spindle, move around according to the DROs, and then drill, say, a hole pattern or whatever it ends up being. So another part of the safety system relates to the startup procedure. So when I switch on at the wall and then switch on at the panel here, this red light comes on, which means it's gone into an e-stop condition, so it's in a holding condition where it won't actually move, and you have to press reset and then the machine is primed and ready to go. If you have an e-stop event, it then goes back into that holding position, so the machine stops and switches off. So it's quite a nice way to implement that, and it makes some of the electronics a bit easier anyway, I think, if you arrange it like that. Okay, so let's see how that and some of the other things are achieved by having a look inside the control box. So first off, it's worth saying that I made my control cabinet out of wood. I had some surplus from a previous project, so it works out very cheap. The metal cabinets I looked at the time were very expensive, but I think they've come down in price now. If you can pick up a metal cabinet, highly recommend that. They're very robust. They do give you some electromagnetic shielding, and they have very convenient features such as knockout panels at the bottom for cables and for cooling fan runs and so on. And they'll often have an e-stop or lockout control on the door itself. But this works fine. The only thing I have to do if I have the door open like this, you'll see I've just jammed in an Allen key in the corner there, just stop it closing so you can see it. I mean, normally it's shut, so it's not a problem. Let's have a look at the philosophy of the layout of this cabinet. I know it looks pretty daunting when you see everything like that. So we'll divide it into little sections. So there's the high voltage AC section from the main, so that's around 230 volts AC in the UK, and that's typically around that area there. We then have the low voltage DC part. That's in this control box, that's the 24 volts, which minimises electrical noise, interference and so on, and that's this region here. And then finally, just for my control box, my breakout board needs 5 volts to run, so I have a 5 volt supply, and that's this region down here. Some of the more advanced control systems or breakout boards will run direct off a 24 volts, so you won't need that. But this is a very, very basic breakout board, and it does need the 5 volt supply. So my overall philosophy here was to separate the different voltage levels, particularly the mains, from the logic side of the system. The other part driving the layout was I've put the two hottest part of the components at the top. So we've got the inverter right up there, and then the power supply for the motor on that side, so any heat's generated goes out the top. The stepper drivers are towards the bottom. We'll come on to this in a bit more detail. And I did have a fan provision for that, but in practice they don't even get warm to the touch, so I've not really been too worried about that. So I've got my hot parts at the top, and everything else is laid out really to try and reduce the interference and keep the mains separate from the signals. So the metal strip you can see up there on the top row and the second row is what's called a DIN rail, and it's an industry standard rail. It enables you to clip on modular units like relays, these terminal blocks, circuit breakers, all sorts of things like that. So between those we have these plastic conduits, and I just unclip this one, give you some idea of how they work. So they come with these sort of flexible fingers that you can push all the cables through. If you need lots of space, you can actually just wiggle them backwards and forwards and snap them off. You can see I've broken a lot of these out. I originally thought I needed a little bit of airflow through there, but I'm not really sure that would have made much difference. And then just to clip it back on again. Simple as that. You just cut those with a hacksaw to the right length, screw them into the board, and give you a nice neat finish on your wiring. Okay, here's a quick overview just going from top to bottom. This is what we have. So we have the inverter in the top left there, and what you'll notice is that I've got that in the top left because it draws air in from the side. I've actually got it coming in through an opening in the side of the cabinet there, and then it goes out through the top. Next along is the line filter. That filters the mains that comes in for the inverter supply there. Next one along is a switch mode power supply to provide the 24 volt signal to the logic supply. And then top right there, this is a linear power supply. Arguably this is the best type of power supply for a CNC machine. You could also have a big heavy duty switch mode power supply as well, but it's generally preferred to have the linear type like this. That drives the stepper motors. So on the next row down we have the earth connections for the outer shield on the spindle. Next one along again is a little DIN rail switch mode power supply. That's the 5 volts down to the breakout board. A couple of through terminals there. Then our first MCB, that's our miniature circuit breaker. That controls power to the 24 volts. Then got our what's called the star earth. So this is where all the earths come together at one point. The next one along is called a contactor. It's like a very sophisticated or a high duty relay effectively. We'll talk about that in a minute. Then there's the miniature circuit breaker, the MCB, that controls that and the linear power supply. Then last on that row we've just got the through terminals that bring the 72 volts DC from the linear supply down towards the stepper drivers. On the next row down we've got, this is a relay for the spindle. This is a spindle inhibit relay, so effectively unless that's on it won't run the spindle, so it's part of the safety control system. The next three along are terminal blocks that give you your 24 volts, which is live 24 volts. So as soon as you switch this panel on here, the 24 volts is live. So that's great if you want to run lighting or the water pump and you want those features to be able to run even if the system is not live. So there's sort of incidental controls, 0 volts. Then you've got the 24 volts, but this time it's switched. So when the system is out of e-stop, that row of 24 volts connections is live, and then you can run other things that require 24 volts when the system is live. Then there's the master relay. So that is the relay that's controlling your e-stop, and it's got a number of terminals on it, or contacts on it, 3 maybe 4, can't quite remember. And once it trips, it allows you to control multiple circuits. So this is just a regular DIN rail mounted relay. You can get proper industrial DIN rail ones for this exact purpose, made by Pilts and other companies. Can be quite expensive, but they are purpose made, and they have some safety features built into them that these don't really have. But as a DIY low duty cycle solution, this seems to work quite well. So you got a choice there, you can go with either. Next along is a relay board. Now I'm using this because many years ago I was having a lot of noise problems on my very long cable runs that went out to, I think I was using micro switches on my limits. This got around that, so effectively everything's done on the limits, on the long cables on the 24 volt side all the way up to this relay, and then the part of the system that just controls the limits signal that goes into the breakout board. The cable is only, well, it's from there down to there, it's about that long, and I've not had any false e-stops on that because that trigger length is very, very long, and it's effectively isolating those two sides of the circuit, the sensing side and the breakout board detection side there. Potentially there will be a very tiny few millisecond delay on relays, but when you're just talking about limit travel, something getting towards the end of the limit, a millisecond doesn't really matter. It's not recommended to do that on probes and homing and so on because of that delay, but on limits I think that's acceptable, and that works for me. As I say, if I had a more expensive breakout board and other features in here, something a bit more high tech, I'm sure I could get away, so I could do away with that, but I've had that in it for years and it works very well. Next one along is the fuse for the control system. I think that's the 24 volt fuse. So next along are the fuses that go to the stepper drivers. So I've got 5 drivers in total. Some of those are doubled up because if I blow the fuse I want it to stop both drivers, not just one, and maybe have the system rack. And then the last one are just some through connections just for neatness, just to keep the power going from the linear supply down to the stepper drivers. And finally, right at the bottom here, we have the 5 stepper drivers. Typically you probably have 3, maybe 4 if you've got some slaved axes. This machine's a little unusual. I've got 2 of my axes are slaved, so I've got a pair on my X and pair on Z. The one in the center is the Y. But they're all the same specification of driver, and they all work in the same way. And then down here, it's a very cheap I think this breakout board came free with the drivers. As I said at the beginning of this video, this machine, or this control panel, is not massively high end, and it's just a very basic system. We've got no relays on there and things like that. Very slow opto couplers, these ones along here. Thing is, it does work. I've had no issues with it at all, other than many years ago I say that I was getting the false e-stops on there, but that's cured that. And when something works, you kind of sort of maybe want to leave it alone. I'm making good parts, so yeah, that's what we've got on this machine. Okay, so let's show you that all working in practice. So we'll just switch on at the wall, and then we switch on the front panel here. Okay, so we've got main power. So we've got our 24 volts is working. We're in our e-stop condition. So if we have a look at the breakout board, so that's saying that's got 5 volts going to it. Green light's on. The relay's saying they're active and ready to go for the limits. Our 5 volt power supply is on. That's our switch mode power supply there in the middle, the meanwhile one. But we're in an e-stop condition, so we're not ready to run yet. So what we'll do in a minute, we'll just press this reset button, and what that will do, it'll throw that contactor across. You'll see that trip across, and then the linear power supply up there will become live, and that will feed power down through the fuses to the stepper drivers, and you'll see those become live as well. So let's just take you in on the contactor. Okay, so 3, 2, 1. So you saw that little indicator move across. You probably heard it come on, and now everything in there is live. and we've got power going to all the stepper drivers. You might have heard the click in there. The master relay is now active. You can see the little green light on it, so that means the system's now live, and should we choose to, we can now run the spindle, because that relay there, the master relay, allows the spindle inhibit relay to run as well. So that's it, we're essentially ready to go.
So while we're talking about control boxes and electronic systems, I'm going to do a short review on this digital oscilloscope sent to me by Banggood. So the usual conditions apply. Banggood have sent this to me to review free of charge, and then I'll give my opinions and summary at the end, and then you guys can decide for yourself. I'll include a link in the description below, and I do get a very small percentage if you click on that and buy. The other thing to mention is that Banggood are having a 13th anniversary sale to celebrate 13 years in business. So between now and the 8th of September, they're having a lead-up sale and a warm-up sale. So there's some promotions on right now. And then on the 9th of September until the 12th of September, they're having a blowout sale. And then from the 12th of September to the 18th of September, they're having an Encore sale. So if you're interested in anything off the Banggood site, go and check out the links and see if there's anything that you're interested in.
Ah, damn it!
So here's the oscilloscope. Now, despite the best efforts of the Postal Service chucking it across the room, it arrived in one piece, all well inside. Here's the unit itself. It's 100 megahertz specification. You've got your 1 gigasample per second, 7-inch display. It's pretty nice. The recording length up to 40k could be a bit of a limitation if you're a really serious user, but for me, I think that's fine. And a host of other functions. There's a few nice warnings on the box, so don't stack more than 6 high. This is the top. This way up. Keep it out of the rain. And a nice glass of wine makes analysis go quicker. It's also in the box. You get the CD, which has got the manual on it. You can also download that. You also get these probes. They're quite nice probes, these. They come with these little coloured rings you can clip on. So once you've done the compensation, you know which one's which. We'll show that a little bit later. Here's the adjustment screw to adjust that compensation. You also get a USB lead. So you can hook it up to the computer as well if you like. Now mine was shipped with this Chinese style plug, which is obviously going to be no good. So I had a look through my adapters. So these are adapters for different markets, and quickly realised actually none of these were going to be any good because I needed a different end. This is a shaver socket adapter for the UK, and yep, that would have worked as well. So that is an option. So then I had to think, had a rummage through my box, and instead of using this, I realised I could just use one of these as a kettle lead adapter to a UK style plug. Sorted. Okay, let's start with a quick overview of the oscilloscope. So this is the model DS05102P. That's digital oscilloscope, 5000 series. It's a 100 megahertz frequency.
They do a 70 and a 200 megahertz version as well, sort of lower and higher in price respectively. So this is a 2-channel scope, so you've got your channel 1, channel 2 there. You've also got the option of having an external trigger down there. It's laid out a little bit like the old CRT scopes, so you've got the vertical and your horizontal positioning. You've got various menu options up here for different measurements. You've got your auto ranging up here, run stop to start and stop the acquisition. You've also got the ability to, so there's a USB port here, there's also one on the rear here, and then it looks like there's a sort of a LAN upgrade that you can have on different models. Not on this one, I'm not too worried about that. Wide range of inputs, so we're 50 Hz in the UK and we're 230 volts there, but 30 watts, so it's a pretty low power consumption device. I don't know if you'll be able to see in there. It's fairly hefty, which is nice, so it won't drop off your bench. Let's see, you might be able to see just there, sort of metal shielding inside it, giving it a little bit of heft, and all the way down there as well, so that's nice to see. And then it's got, at the rear, it's got these little rubber feet, and then at the front, these nice flip up feet there that make it sit nicely on the bench. might help if I switch it onto the wall. Hold on. Okay, I'll switch on. Just takes a few seconds. Okay, so now we've got the unit on. The first thing to note is the really nice bright display here. This is a 7-inch display, so it's really quite large here. And unlike some older models, you can turn the menu on and off at the side here, which means you get that complete real estate to look at your waveform. Also on here is a number of very small symbols all the way around that give you lots of information about what mode you're in and where you're at. So starting at the top left corner, this one means we're in what's called YT format, so we're just looking at time history, so time along here and amplitude along here. The other format to be in is XY mode, and that's where channel 1 dictates the X and channel 2 dictates the Y, and you can end up with kind of looking at the phase information between those two channels, probably a little bit like a Bode plot. The second one along is vectors. That's about how you're displaying your waveform, whether you're joining up the dots with lines or just looking at the dots. Next one along is something called auto persist. That just holds onto the signal a little longer on the screen just to make it a little bit more visible. Next one along is trigger. We're currently in auto trigger mode and it's just in automatically triggering there. There's a few grayed out items, but you may just be able to see those. Those will appear when you've got a disk installed, a USB drive installed. Next one along is the waveform and relating to the memory inside and how much of that you can see. Next one is the time base. This one shows DC or AC coupling, whether you're interested in the DC or AC parts. The next one's grayed out, but that will light up if you've limited it to 20 MHz bandwidth. Next one shows if your signal's inverted or not. Then the trigger itself, this is currently showing that it's on a rising edge trigger. And then this one down here is the frequency count. We've got date and time also down the bottom here. Right, let's hook up one of the probes. So this is the probe here. It's got a quite nice feel to it. The switch feels okay. That's your ×1 ×10 switch. So in the ×1 position you're limited to about 6 MHz, which might be okay if you're just messing around with something very simple. If you need the full 100 MHz range that this scope offers, then you need to go into the ×10. They come with these little color coding strips, and just show you that. They come with these colored clips here, and the idea is that once you've calibrated this, you nominate it to a channel. So in this case, this sort of channel here is the yellow one. So this is everything to do with yellow, channel 1, and channel 2 is the blue. So once you've dedicated something to that, you clip the right color on and keep it with that, so then that calibration remains true. Right, so speaking of calibration, we'll just plug this in. Just before I do that, you'll notice in there's a little trim pot, because what we're going to do, we'll just plug this in, and then on this side we've got a 5 volts 1 kHz square wave signal. It's like a kind of reference signal, so we'll put the ground on there, and then the pull back up. And then if we do run stop, and there's our square wave. Obviously you'll notice it's not quite perfect, so there's something called undercompensation and overcompensation. So we need to get our little tool out. It's got a tiny little screwdriver on the end, and we'll just adjust that until we get a nice square wave. So it would be somewhere around there. If we go too far, it looks like that. Something like that. Before I take that off, just one more thing. So we're currently in live mode. So if I hit the run stop, we'll now be stopped. And a little symbol appears up here, a little red symbol here. We're now in sort of a frozen offline mode. So if we take those off, the signal remains. So before we forget, what we'll do, we'll put the coloured tab on here, the yellow tab. Yellow tabs or rings. So now we know that one's calibrated for that. get our run stopped, go back into live, and there we go there. Nice clean signals. So those are our vertical positions for channel 1. We've got the same for channel 2. I won't show you that, but it's basically the same. We've then got the horizontal position. So now we're looking at our divisions in the x-axis. So let's try and so we can zoom in that way. We can zoom out. You'll notice the microseconds is changing up here. This is how many seconds per division we're essentially changing. Zooming out a long way there. And then we can zoom all the way in again. And in the same way that we can tune the position in the vertical sense, we can tune it horizontally as well. So we can move this signal along. Get our pulse right in the middle if we wanted to. There we are. Now let's see how far we can actually zoom in. I think it's 2 or 4. There we are. So we're now zoomed in. You may just be able to read that. 2 microseconds, so pretty well zoomed in there. And then we can zoom all the way out again. Okay, now the scope's been on a little while and it's warmed up. What we'll do now is do a self-calibration. So to do that we need to take probe out and then we go into utility and we've got a range of options here. So system information, firmware update, save the waveform, self-calibration, so that's the one we want there, and that is under F4. Press that. Disconnect all probes, so we've done that. So it's channel 1 to an external trigger, and then F5 to confirm. It is warning you don't turn off the power during the self-calibration, so let's get on with it. Let's do confirm, which is down here, F5. I'll bring you back when it's done. Okay, well that took about 10 minutes to go through the calibration, and it went through AC, DC coupling, some different voltage ranges, and there were relays clicking in and out as it's going through the different settings. So now it's finished. So we should be able to come out of that. Before we do that, let's just have a look at what else is on offer in here. So I'm just going to flick through these. Okay. Oh, we can have a keypad beep. That would probably be annoying, so we'll leave that off. GUI color. Let's try that one. That's quite nice. So we're getting a little bit of like more fringes or something on the camera. Let's try. Okay, that's black. Green, yeah, okay. Pink, lovely. Yellow, blue. Okay, so we'll hook the probe back up to get a reference signal. Okay, and there's our nice square wave again. That's our 1 kHz 5-volt signal down there. So yep, now we've just pressed display, so we can have a range of different display types. So we got vectors or dots. So the dots are the actual positions it's measuring that signal, but then the vectors it's drawing straight lines between them, which I think looks quite nice. Contrast down the bottom. Now it's worth pointing out, sometimes when you're in a menu function like that, this little green light comes on, and that means this scroll wheel is active to give you some functionality there. So when we move that scroll wheel, we're adjusting the contrast, and hopefully you can see on the screen. Yeah, so I think it came in about 8. That looks a little bit bright there, doesn't it? Maybe leave it on the default on 8. Then on the next page we've got, okay, the grids themselves. So currently they're dots and they're relatively faint. Let's go on to the grid intensity first so you can actually see them. So we'll go on to that one. Now that's lit up, and again little green lights on so we can move that around. So let's make them very bright. It's very bright looking at it for real. If we go back down again, they almost fade to nothing. You do want some kind of grid on because you usually want to read off the scale, so we'll put that on. Put that on there. So once, let's just make them a little bit brighter. If we just try now going on to this one, yeah, get actual lines between them, or you could turn them off altogether. I think the dotted default is the best one there. We've got refresh down here, and we can also change the intensity of the waveform itself. So let's scroll down to that one, and again our wheel is active. I can make it very dim, or pretty bright. I think it's somewhere around there. Yeah, somewhere around there. It looks pretty good. Okay, so explore the functionality of the oscilloscope a little bit further. I've hooked it up to my function generator. This is an arbitrary function generator made by RS. So this is my own device, and then the oscilloscope's been given to me for this review by Banggood. So this will put out sine waves, square waves, sawtooth waves, random white noise, and it'll also put out an arbitrary signal that you can define via a PC and download it into the back of the machine. But we won't go into that here today, we'll just use the basic functionality. So you can define the frequency and the amplitude peak to peak and a whole host of other things like offsets and duty cycles and so on. So it's quite a handy little bit of kit. So we're going to use that just to try out, demonstrate some of the functions within the oscilloscope. So first of all, we'll hook up the CNC cable. So the first thing we'll do is explore the channel 1 menu. Okay, and that looks like this. So we've got our coupling ranges at the top, whether we're DC or AC coupled. Currently we're DC coupled, which means we're seeing the whole signal. The AC would just be the ripple on top of that. We've got our 20 megahertz limit off, so we're measuring the full 100 megahertz at the moment. We're currently on our coarse volts per division, but we could change that to fine. Down here is our probe multiplier, so we're currently running at probe times 1. You have to be careful with this oscilloscope because it doesn't have the automatic detect on the probe. If you're in times 1 or times 10 position, you have to manually go in here and tell it which one you're on. If you want that to be automatic, you have to pay quite a lot more for your oscilloscope, so just be aware of that. Then the last one down here is whether you are going to invert the signal or not. Okay, so the next menu we're going to have a look at is the trigger menu, and that is over here underneath this knob here. So we press that, and in here you can see the various types of trigger that are available. So you can trigger off an edge, a rising or falling edge, a pulse. If you've got a video signal, you can trigger off one of the components of the video signal. Down here we've got our source, so the source we're going to trigger off. At the moment we're on channel 1. We could trigger off channel 2. There's some external ones. If the external voltage is too high, there's a divide by 5, so you can bring that voltage down. And then you've also got the ability to trigger off the AC signal coming in through the power cord, so you could trigger off an event that happened on the ring main or something like that. In terms of your slope, you can trigger off the rising or falling, and then just for the trigger you've got this coupling mode here, so you can either DC or AC couple. So DC means you're seeing the whole signal, AC is just the ripple above about 20 Hertz I think it is. Now just be aware this is the coupling for the trigger only. Once you're triggered, the coupling that will be applied is the one you've got down here, which is currently DC as well. So that's the trigger menu. While we're talking about triggers, I'll just move this knob here, and what you'll see is a green line appear, and we're currently triggering at 0 volts. So as soon as we pass the 0 volts, we've got that trigger event. So if I'll just rotate this dial, you'll see this green line move up and down, and now you can see that we're triggering off, let's say 1 volt here. So that's quite a nice visual way to see exactly where you're triggering. With the number of these knobs, if you press them in, they go back to kind of a default. You might just be able to see that it's gone back to the middle there to 0. So that's the trigger menu. So one of the other features we got on here is under this F7 button. So if we press that, brings up our trigger menu again, and then we can see quite a large part of the waveform here, and then we've zoomed in on a piece here. You can apply various things like markers and all sorts in that menu. Go back to single. So another menu we've got is the horizontal menu. In there you can set some markers on either the major or the minor window, and you can also play around with the time divisions, make them fine or coarse. Another pretty fun little menu actually is this math menu down here between the channel 1 and channel 2 menus. So if we go into there, okay, now we can do various operations on channel 1 and channel 2. So here we're adding them together. Now we're obviously not putting anything into channel 2, so it's going to look a bit strange. But this gives you the ability to look at the differences between the two channels if you're probing a circuit or something like that. So you can add them together, you can take them away, 2 minus 1. Also it's going to look a bit strange because we haven't got anything in that one. Times them together, divide them. Ooh. Okay, the last one down here is FFT, so this stands for Fast Fourier Transform. And this is a way of looking at the frequency content inside any kind of time history, waveform. A couple of things to note about FFTs in general, not to do with the scope, but just FFTs in general. First thing is, because the window that it's going to take to do the FFT on in the time domain, in the waveform, it wouldn't necessarily start and stop at 0. That causes something called leakage in the processing, and it acts a little bit like an impact, and it sprays the spectrum with some high frequency noise, and you get lots of errors. So you have to window that data to bring it down to 0, or ensure it starts and stops at 0 within that frame. So Hanning is quite a nice one to do if you're looking at sine type input. If you've got an impact, you might want to do a rectangular. Just bear in mind whichever one you're picking has some pros and cons about the accuracy for frequency or for amplitude, so just make sure you're picking the right window. The second thing to say is, like any FFT analysis, not just this scope, you have to make sure that you're sampling at least twice as high as the highest frequency that's present in your signal. If you don't do that and you've got frequencies higher than that are close or somewhere close to your sampling frequency, you'll get what's called aliasing, and these will fold back and give you spurious alias signals. So you have to sample at twice the frequency of your highest content, which is called the Nyquist frequency. So you need to be twice that Nyquist frequency to avoid that error. So that's, again, not to do with the scope, just general FFT processing. So those are general FFT things to be aware of. Something specific to this scope is it's only got 1024 lines. So if you're doing a very detailed FFT analysis with a lot of content, you may miss anything that sort of drops down into the noise floor, or it might be too thin to give you the resolution. But I've been playing around with this, and actually for general use it's pretty good. But just be aware you've got 1024 lines on this scope. Okay, so we'll put 10 kilohertz up here. Then we can see on here, so each one of these major increments here is 5 kilohertz. We've got 5, 10. So there's our 10 kilohertz signal coming through in the frequency domain. Okay, so the next thing we're going to do, we're just going to try a square wave. And the theory of signal processing says that you can replicate any time history or any waveform like that by breaking it down into a number of harmonics and frequency contents of different amplitudes and different frequencies, that if you converted them into time and added them all up, you would get somewhere close to the original waveform. So for a sine wave, clearly you've just got that one frequency there. For a square wave, it's represented in the frequency domain as some major frequency and then lots of harmonics of that with decreasing amplitude that goes off into the distance over here. And if you were to add all those back up and convert them to time, you would get your square wave back again. So let's set this to a square wave and have a look to see what the scope generates. So we need to go to the next one. So this is a 10 kilohertz square wave, and the harmonics are plenty, so let's zoom out. There we go. So when we've got a square wave, it's a series of all these harmonics that decrease in amplitude like that. So that's giving us our representation in the frequency domain. So that works fine. The other function we can try on here is we've got our sawtooth. So again, this is what a sawtooth would look like in frequency content, and then white noise. Which, yeah, okay, just looks like white noise. Okay, so we'll take ourselves back round to sine wave again, and come out of the maths menu. Okay, so now we've come back into our waveform mode, and we've got our 10 kHz signal on the screen here. One other thing just to note is that whenever you're in any particular menu, there is a help button here that brings up a context sensitive help. It gives you a little bit more guidance on what you need to do. If you've been messing around and playing with some of the parameters and you want to go back, you can go to a default setup up here, and you can also save to a USB on this button here. Okay, so let's summarise this scope. So it retails for around £250 usually. At the time of this review, it's currently on sale for just under 200, it's about £196. And for that, I think you're getting a really nice scope. You've got this lovely display here, it's got a quick update, it's got a nice user interface, it's easy to understand where all the controls are and what they all do. You soon get up to speed with it. It seems to have a lot of functions in it, a lot of built-in functionality, lots of options. The only two drawbacks I think I mentioned during the review of this were, the first one was the memory size is limited to 40 kilobytes. I must admit I've not really run into that as a limitation during playing with it, but that's something to think about if you for a bit of a power user. So the second thing to mention is the FFT calculation on this is limited to 1024 points, 1024 lines. So if you're analysing some particularly high frequency content signals with lots of information in it, maybe you'll lose some of the finer detail in that. But I must admit, playing with it, I've not really seen that as a serious drawback. I think it's probably best to consider this as a pretty usable, fairly powerful scope with a little bit of FFT analysis added on. If you're really serious about doing FFT analysis, you can always output the acquisition to your PC and run some kind of dedicated FFT analysis on there, where you're only really limited then by the PC power. So you've got options. So a scope is not a casual sort of whim purchase. It's something you want to think about and you want to research and look at all the different options and look at competitors, the Regal scopes and others as well. So I think all I'd say is have a look at the features of this one, have a look at the price, have a little look through this review that I've just presented here, and then make your own mind up. But I'd certainly put it on the list of considerations, because I think it's a great little scope, and it's going to make a great addition to my workshop for diagnosing various electronic issues.